Okay, I'll try to quickly go over a bunch of the important details for the RNN lecture. I'll try to summarize it as much as I can. Um, the book already does go over a lot of details, but there are a bunch of other resources that I found that were super helpful in understanding the lecture and like explaining it in a lot of detail. Like this article, for example, this was the main one that the doctor was using as like a reference for the book. A lot of things are very similar. So I'll have linked those resources by now. They make a lot of things like really clear. But yeah, I'll try to follow as closely to the book as I can and connect the dots. But just going straight into it, the first part of the lecture was like more theory oriented. So why exactly do we need RNNs and why do we use sequential models? The main point is that the input data has now changed. Instead of using numerical data and image data like we've been doing before, we are now going to try to use text and speech data. And before, we didn't really have an issue with the architecture because of two main factors. The first one being our data was independent, so there was no issue at all of like dependency between the data. When working with images, for example, each image in the dataset was its own image. We didn't necessarily have to know any meaning or context behind that image and the other images around it. The model didn't need to know any of those details. They could be linked, they could be completely different. It did not matter. And the second thing was the fixed size of the data. So uh, for images, once again, for example, they had a fixed dimension that we knew beforehand, and that was really important when building our model. If we didn't know the dimensions of the image, we wouldn't necessarily be able to build all of the layers since we need to know the input going in and the output that will return. So these two things kind of change with text data. So when working with text or speech, the data is ordered and it is sequential. So there is meaning to the ordering of the data. So the first point being that like it is no longer fixed size. So the size is now dynamic. The user can enter whatever they want in terms of like sentence length. They can enter 10 words in a sentence, 100 words, 1,000 words. The model should be able to handle it. Obviously, it will be varying results, but the model should be able to understand that, and it doesn't necessarily need to expect a fixed size for the data. And the second thing being that the inputs will be dependent on each other. So when working with sentences, and especially when working with something like semantics, trying to understand the meaning of the sentence, it is important to know what exactly each word means in relation to the others. So like with this sentence, for example, what exactly does this word mean in relation to the one before it and in relation to the sentence as a whole? So yeah, these 2 points kind of force us to change the architecture of the model. And the main idea is that we want to somehow input a or implement a memory architecture for our model. So how do we do that? Through the hidden states. We're no longer going to be using the traditional idea of input to hidden layer to y to output, where there's a weight here and weight here. Our hidden layer is now going to be called a hidden state, and it is going to be connected to the other hidden states. Instead of h being just the hypothesis function of the inputs, just being w times x plus bias, it is now going to be a function of the other hidden states. So this is also in the book as well. Um, yeah, right here. So h of t is going to be a function of the inputs x and h of t minus 1, the hidden state before it as well. So each hidden state is connected to the one beforehand. This acts as the memory for our model. So everything is now a lot more connected together. And since we want to connect them together, they are going to have their own weights. Whenever we want to try to learn something, we're going to introduce a parameter to it. So instead of just having weights here and weights here, we're going to have an additional matrix of weights for our hidden states and each other. So this kind of architecture changes a lot. We are no longer going to be working with this multi-layer approach of building a lot of hidden layers between our inputs and outputs. This is just a single layer, just a single input node, a single hidden state, and a single output node. And we're going to pass all of our input through this one layer. We can build multiple layers, but just in this example, we're going to use a single layer, and we're going to unfold this layer over time. So all of these aren't different layers, they are just the same layer at different time steps, at different input points. So for example, if we use the sentence, a simple RNN comprises of 3 layers, that is going to be, each word is going to be at its own time step. So for example, is going to be the first time step, simple is going to be the second one, RNN is going to be the third one, and so on. But each of these is the same exact layer. So these weights are shared between all of the layers. They aren't going to change between them. Like, we aren't going to have a separate weight matrix for each input. That would get way too complex. So this kind of saves us a lot of time and a lot of computation power. But the whole architecture idea changes. We're no longer going along with this layered sort of architecture, at least in this example. So yeah, that is the main idea of it as like an intuition point of view. But going into the equations, going to the forward path, we can kind of look through this diagram as well, which breaks it down even more into further parts. So at the beginning, we have our x as an input going into the hidden state, and normally before we would just do w times x plus b, but here we have to keep in mind that h has 2 inputs now. So h of t here, for example, has x as the input, but it also has h of t minus 1 as an input. So this will also be w of h times h of t minus 1 plus wx times x plus bias. So this is the hypothesis or the pre-activation of the hidden state. Each hidden state is going to have this equation. So we can define z h of t as w of h times h plus w of x times x plus bias, and then we'll apply another nonlinearity to this hidden state. So traditionally, it's just tan h that is used for RNNs. The other hidden layers should work as well, but we don't necessarily have to know the details or the differences between them in RNNs. We're just going to be sticking with tan h. So the tan h of this pre-activation is going to be the output of this hidden layer, or this hidden state, sorry. And then after the hidden state, we're going to keep moving forward to the output. So this is going to have its own weight now. So wy times h plus the bias. Each sort of step has its own bias, but we're not going to focus on the bias that much. But yeah, this is going to be the pre-activation of the output. And then once again with the output, we're going to have an activation function so we can predict probabilities. We're going to use softmax. So we're maybe already kind of intuitively apparent, but we're trying to predict a word from a vocabulary in each time step. So the vocabulary is going to be a whole bunch of words or a whole bunch of letters, for example. Like here in this example, we're trying to predict each letter in a word, and we're inputting the word deep, D-E-E-P. So our vocabulary is D-E-P and stop as like an end of sequence, and we're trying to predict the sequence of words or the sequence of letters depending on the input. So in the first input, we have D, and we're supposed to predict 1 0 0 0. There's a mistake in this diagram. It's supposed to be 1 0 0 0, but we're trying to predict each single letter in every word. So at every time step, we're going to have a separate output. And this will be apparent as we go through the backpropagation as well. But we are no longer going to have one single output. We're going to have an output for each time step. So there's an output here, there's an output here, and there's an output here. Which also means there's a loss here, or an error here, an error here, and an error here. But we'll look through that in the backpropagation part. But for now, in the forward propagation, at every time step, we're going to have this pre-activation, so the weight of y times h, and then that is going to go to the softmax for y, and then we'll output this one hot encoded vector of probabilities. So yeah, that will be our forward propagation, and the loss will obviously be categorical loss. So since we're using softmax, we'll be using categorical cross entropy, and it will work in the exact same way, where we're going to have a summation over all of the classes for like however many classes we have, and LT being the true or target class that we want, and we're going to calculate log of y. It will be the exact same concept, But once again, we're gonna do a summation over all of the time steps because this isn't just a single layer or a single output at the end. This is gonna be multiple time steps. So we're gonna do the same thing. There should be another summation here, but we're gonna do a summation of all of the outputs times the true one, and then sum that over all of the targets or all of the time steps. Sorry. So just going through the forward propagation again, it's just going to be z h of t, and then that is the pre-activation for the hidden state, which will be tan h z h of t, and then from that we're going to take h of t multiplied by the weight, and then from that we're going to apply softmax on it, and from that we can apply the loss on it, and that is basically the same steps that we've been doing for forward propagation before, but now we've introduced this hidden state that has its own activation. And that kind of makes things a lot more complex, but we have to do that to kind of soften and dampen the effects of the hidden states, so the numbers don't expand out of control. But yeah, that is basically the forward propagation part.